Hey students, aka welcome here. We're going to do our last chapter on optics. It's called The Wave Nature. It's chapter number 27. And in fact, let me put it here on the board because due to time constraints, as you saw in the last video lecture, we're not going to do every section. And so we're going to do chapter 27, section 1. And section 2, and then we'll do section 3 and section 4. And in fact, these kind of group together, so I'm going to make a little video of these two and then kind of pause. And then later on today, I'll make 3 and 4. And I've already made a video for section 8. But those are the 5 sections we're going to do here for this chapter. So it's quite a few, but very reasonable before we switch gears and leave optics and go into our last unit, which is modern physics. But this first part, which I will call 27.1, is called The Wave Nature of Light. And so in the last 2 chapters on optics, we've done geometric stuff, and we've treated the light as rays. That is, they travel in a straight line until they either reflect or refract. Now we're going to look at some of the properties of the waves. And so I'm going to ask you to kind of go back to your Physics 110 at the end where you did things like sound waves and you learned some properties of waves. And in fact, I'm going to have you go back even a little bit earlier in this semester and talk about the electromagnetic wave, or at least show you a picture here, because when we deal with light waves, we're going to say the human eye can pick up light within this band of about 400 nanometers to 700 nanometers. In fact, come with me. I put up the camera here, or the textbook in the PDF form here. And back here in chapter 24, and it's figure 16, we talked a little bit about this visible light. And so in this chapter, we talked about the whole general idea of electromagnetic waves. And so for us in this chapter, keep in mind then we have these different wavelengths. Also, I want you to notice in your author's picture, he's got something very useful and interesting. Notice that his graph counts down in wavelength. He's got a little arrowhead counting down. And the reason he does that, let me come back over to here, is because going back to Physics 110, you might remember that velocity equals wavelength times frequency. And so if we multiply those two together, we could make a plot that either has frequency or wavelength. But notice they're the opposite of each other. They're what we would call inversely proportional. So in other words, the speed of light, which we will give the common notation of c to, and I should say this is the speed of light in a vacuum, is roughly 3.00 times 10 to the 8th meters per second. I guess a little more accurately, it's, 299, it must be 792, 458 meters per second. And maybe I should just confirm that, 792, 458. What I'm going to ask of you is you commit this to memory that it is roughly 3 times 10 to the 8th meters per second. Now, mathematically, what I want you to show you is that if this is a constant, when one increases, the other must decrease. So most people like to see the rainbow, if you will, from low frequency to high frequency, even when they're listing wavelengths. So That's why, I'll come back to your textbook, your author does something quite interesting. He has a number line that is decreasing in wavelength. To me, that's kind of confusing. So if you want to list it from red to violet, which I do, I'm going to do this. I'm going to say over here will be my low frequencies, red, and over here will be my high frequencies, violet. And let me just pause right there. That's what the human eye detects. If you remember when we did our acoustics, we said the human ear can pick up different frequencies, and it gets registered in your brain as different pitches or different tones. The same thing happens with your eyes. Your eyes can pick up different frequencies, and it gets registered in your brain as different colors. And so if somebody were to ask, what's the difference between red, green, and blue light? Well, the answer is there are different frequencies / different wavelengths. That's the difference. And so we are going to include our wave nature, and we're just going to say all the light has the same general behavior. They act as waves. But they do have a different frequency, or they do have a different wavelength. And so what's very useful is this acronym that it sounds like somebody's name, because the first three are Roy. And the middle initial is G, and the last name is Biv. And so to help you remember the spectrum, we're going to call it Roy G Biv. Now, of course, if you list the wavelengths this way, the long wavelengths would be red, then going to orange, then going to yellow, then to green, then to blue, then to indigo, and then to violet. So the shortest wavelengths are violet, the longest are red. It doesn't look well on a graph like this showing Roy G Biv. It looks better on a frequency graph, unless you take a graph and come back over here to the screen and label it this way. But you can see how your author is taking this, and he's going, here's your Roy, your red to orange, your yellow. And so yellow around the 600. Then he goes to green, then blue. And he doesn't really list an indigo, kind of a transition between the blue and the violet, and then the violet. So he's got the 6 listed here. And so, like I said, just kind of wanted to take you back a little bit and do a little bit of math with you here. So if I were to tell you that the wavelengths are from the short ones, violet, 400 nanometers, to the long wavelengths, 700 nanometers, what would that be on the frequency scale? And this is where I'm going to take advantage of this equation, which, like I said, we did last semester. And so I would write this equation. I would say the frequency is the speed of light divided by its wavelength. So if I wanted to do the frequency of red, and then also see, what is the frequency of violets, I would do something like this. I would say take 3 times 10 to the 8th meters per second and divide it by the wavelength of red, which I'm saying is about 700, and let me pause, nanometers. Yeah, if you remember way back to chapter 1, a nano is 10 to the minus 9th. I bumped it wrong. Check my sound. But this would be 10 to the minus 9 meters. So if I go ahead and grab my calculator here, I would have then meters canceling off. I would be left with 1 over seconds, which is called a hertz. And so if I go 3 times 10 to the 8th and divide it by 700 times 10 to the minus 9, I get about a 4.3 times 10 to the 14, or 430 terahertz. And so right here at the red is the low frequency, which 430 terahertz, if you want to call that low. But this is the lower that your eyes can detect. 4.3 times 10 to the 14 hertz. Now on the high side, we would have this, 3 times 10 to the 8th meters per second divided by 400 nanometers. And so this would be 3 times 10 to the 8th divided by 400 times 10 to the minus 9. And we're looking at 7.5 times 10 to the 14 hertz, or 750 terahertz. So I will put that over here, 7.5 times 10 to the 14. Well, I don't have to put hertz, I guess, because I've got it in my number line. So I'll say it again. The whole point of this first little section is to remind you that light is a wave. And therefore, there must be some kind of wavelength, associated frequency, and mathematically then a calculation that connects wavelength and frequency together. And in fact, while I'm here in chapter 24, let me scroll down to another figure you saw in chapter 24. It's number 23 here, because when it says what's going on here, we're going to draw this picture. We're going to draw a wave. And so kind of like we drew with sound waves and water waves last semester, we're going to do something that looks like this. And of course, it's a natural question to say, well, what's waving? Well, now you can see why our optics followed behind our electricity and magnetism, because the thing that's waving is both an electric field as well as a magnetic field. And I don't know if you can see this well in this picture, but I want to emphasize this, that you've got to see this in three-dimensional space. In other words, the wave travels along this direction. Let's call it the x-axis. And so for you guys on the video, let me call that is the direction of the light. That's the x-axis. And so the electric field is vibrating this way, call it the y-axis. And the magnetic field is vibrating this way, which is the z-axis. So the electric field and the magnetic field are perpendicular to each other. And then those are each perpendicular to the direction that it travels. And that's this wave nature. And again, that's what this section here is really all about. What is this wave nature? Now let me pause for a moment, because again, we're going to go back to last semester a few times here, because we learned some nice things about waves, and we learned them again last semester, but let me just kind of remind you of them. I'm going to come over here and grab this machine here. We call this a little wave machine, because the part I want to remind you about is what we call the superpositioning. In fact, maybe I should draw it on the board here. Let me come back over here to the board. What would happen if I had a wave, and I'll just call it a wave pulse, that is traveling to the right, and another wave pulse that is traveling to the left? Because when they meet, you're going to get the sum of the two. They're both saying up. And then they pass through each other on their own little way. And we call that the superposition. positioning. And so we just add them together. Now, I can kind of show you this with our little wave machine to remind you, but we're going to do a lot of that in this lecture, especially in section 4. And so I'm going to make a little pulse, let it go to the end, there it goes, and then a second one, and watch when they meet. Here they come, meet. Here they come again, meet. And see, right when they meet, you just get the superpositioning. You get the sum of the two. Oh, I'll do it one more time. All right, so I'll make a pulse, it'll go to the end, and then I'll make another one, and then right where they meet, see how it gets like enormously big? Because it's the sum of the two. And then they like pass right through each other, so they don't bounce off each other. And we called that the superpositioning when we were back and doing our acoustics. So that is an important part of waves. And so I wanted to remind you of that. In fact, as long as I'm here, let me make some sound waves also. What would happen if I did something that looked like this? What if I had one wave that looked like this? And let's just say it's traveling towards you. And in this case, towards you will be the microphone on the camera. So I'm going to have this going towards the microphone. Or I guess actually it'll go towards the microphone on me, which will then get sent to the camera. And then if I had another wave that looked like this, what would I get when those two meet? And I'm hoping you can kind of see what we would call constructive interference last semester. We would have the superpositioning of both these waves. This would be an up and that would be an up, and the result would be a big up. And then over here, this one would be down and that one would be down, and the result would be a big down. And so I've purposely drawn these two waves so that each of the ups matched and each of the downs. And so the crests match crests and the troughs match troughs. And you get a result of a very big wave. Now compare that to this. What if I had a wave, and so let me take the original wave that looks like this, and a second wave that goes down first and then up. So it has a trough, then a crest, and then a trough, and then a crest, and then a trough. And I combine those two together. Now, this crest together with that trough would get a result of 0. And as we go through this, this trough with this crest would give you another 0. And then this crest with this trough would give you another 0. In other words, what we would get is a destructive interference. But notice it's still the same results, that I'm just adding them together. In this case, I'm adding a positive and a negative, whereas over here, I've added 2 positives or 2 negatives, 2 positives or 2 negatives. Here I always have 1 positive and 1 negative. And just to remind you of this is kind of easy to do in a classroom like this, because what I can do is make 2 waves and then make one go a little bit further than the other. And so when the 2 come together, then they can line up crest with crest or crest with trough. And let's come over here to this weird looking blue thing here. And maybe for lighting, Ron, I'll turn that off. I think that'll help the lighting here at the angle you're at. But I've got a little microphone here, or a little speaker. In fact, let me get it a little closer to my electronic gear, because I got to plug this in. But if I turn this on, hopefully it sounds obnoxiously loud right now. And see, what's happening is the sound waves come up and they split into two along this tube, and one goes this longer path and one goes this shorter path, but I've set it up so that the two crests come together and it's really loud. You're getting this first case where I have constructive interference. And just kind of to show you, let me turn it on again. Oh. And I'll just put my hand over the top of this to kind of convince you that the sound's coming out of this hole. Okay? And it's really loud. But watch this. What if I'll turn it off here for a second. What if I made this path a little bit longer? What if I made it a half wavelength longer? So that by the time the waves go down here, it's matching the opposite from here. So in other words, when a crest is coming out here, I get a trough here. And then I would get the second case where I have destructive interference. And hopefully you can hear it on camera with the intensity. And so I'm going to pull this tube, which will make it a little longer. And right about there, I have now made this go an extra half wavelength. So that means this distance plus this distance, because that would be the extra distance it traveled, is a half wavelength. And I get destructive interference. Well, I better not spend too much time here with our acoustic, because we did that last semester. But I do want to kind of remind you of it, because we're going to use that information and that same pattern about constructive and destructive interference, but now we're going to do light waves instead of sound waves. Now, that's what sections 3 and 4 are all about. And so that's why I wanted to take a moment here and mention the wave nature. Now, let me turn the screen here back on. Let me give myself a little bit of space here on the whiteboard, and let me just keep talking about section 1, because section 1, like I said, is this introduction to the wave properties of light. And the wave properties, I would say, aren't any different than the wave properties we did for sound waves, although it was last semester, so it probably is worth reminding you of that. Now, let's talk about something else kind of nice. We learned that we did learn in the previous chapter, I think it was 2 chapters ago, that when light goes through a medium, such as glass, it slows down a little bit. So in other words, we had this. We said, okay, if you had air here, and maybe glass here, and we said, okay, here is this beam of light. And we said, well, what would be its speed? We would say c divided by the index of that material. We call it the index of refraction. Sometimes we call it the index of speed. For air, it would come out to be 3 times 10 to the 8th divided by 1.00029. And so, like we did in the past chapters, we could pretty much say air has an index of just 1. And so I'm going to say that the speed of light in air is about 3 times 10 to the 8th. But as you know, when it enters glass, which has an index of 1.5, of course it also kind of depends on what glass we have. But I'll just pick on crown glass, common glass. This would be 3 times 10 to the 8th divided by 1.5, which makes about 2 times 10 to the 8th meters per second. And so clearly it goes much slower. Now that's not new. That's something we've done for the last 2 chapters. But what is new when we put this in with the wave nature is we have this. On this side of the equation, we have something that looks like this. C equals to wavelength times frequency. And on the other side, where we go into the glass, we have reduced the speed by a factor of n. So we would have to divide the other side by a factor of n. Which then brings up this question, if the speed was reduced by a factor of n, was it the wavelength that reduced by a factor, or was it the frequency that reduced by a factor? And it turns out that it's the wavelength, and you can probably see this in a picture if I do this. Let me put this boundary again. Here is the air, here is the glass. And maybe I'll just kind of draw kind of a little squirrely wave down here. And maybe I'll represent right here this vertical line to be all the places where there's a crest. And so what happens as the light enters, this electric field gets over here to the surface, and the electric field is changing at some rate, that's the frequency, and it then generates, if you will, crests over here, and they move away. But notice they would be moving away at a lower speed, and that's why this wavelength would be reduced to a smaller value. And so let me take this as a moment to say it is not the frequency. You can see that in this fashion, that these are being generated by the electric field that is oscillating due to here. So these are going to have the same frequency as those. And in fact, as we get into modern physics, we'll make another argument that the energy is related to the frequency. So it can't be the frequency. That would violate conservation of energy. So what gets smaller is its wavelength. So my little equation here is that the wavelength in glass or in any medium is reduced by this factor of n compared to what it is in the vacuum, or we could even say in the air. And so this is my, I guess, my way of demonstrating that we have yet another equation. And so I guess we have a couple of equations that are probably worth putting here on a kind of a summary. This is that beginning part. That these are our three equations relating the speed of light, the wavelength, the frequency, and of course now we're seeing that the wavelength gets reduced by a factor of n. Now that pretty much wraps up section 1. Let me jump into section 2, and then I'll do some examples from section 1 and 2 here. But section 2 of your book is Huygens principle. Now, this is more of a conceptual picture than it is mathematical. And so, as you'll see when I turn to the back of the chapter to do some examples for you, there won't be any calculations to do for section 2. But it's an important principle here, and let me then show you more by pictures than anything else. And so let me come back to your textbook here. Let me go to section 2 of your book. Whoops, I went too far. Hang on here. chapter 27, okay, section 2, right here. And so in section 2, Huygens makes this argument. And I think the best figure to kind of look at first is really down here. Huygens was using light waves, and he said, let's take some light waves, and so that's what this picture is trying to represent, that these are the crest of the waves, and he lets them entering a small hole. And he sees that they kind of spread out a little bit. By the way, that spreading out is called diffraction. And then he makes the hole smaller and smaller and smaller. And that's what these three pictures are trying to illustrate. These three pictures are trying to say that if you take this and you make it even smaller, what you'll get is kind of this light spreading out. Ultimately, when you get to a really, 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 really fine little point, you get this full, equally spread. So here was Huygens' idea. Huygens' idea and Huygens' principle is along these lines, that every little place of a wave is really the start of a new wave, and the result you get is the superpositioning of that. Well, let me explain. And so let's just take a wave that goes straight across. A wave that goes straight across, then, these points right here would each generate an equal wave coming out. And so you might say what we have is an infinite number of little tiny wavelets. And if you do the superpositioning on them, you get another wave front. And so a solid line makes another solid line, makes another solid line, and makes another solid line. So it's nothing real revolutionary, but it is going to be important in the next couple of sections that we remember we can always think of a wave as being made up of an infinite number of little wavelets. And Huygens uses that to explain things like, why does the light reflect off of a mirror? Why does the light refract? Let me go back to this picture. This is why it diffracts. He says, look, if this wave comes in and then you have barriers right here and you chop it off, then you just have a bunch of little points, but they don't go on forever. And so as they spread out, the ones in the middle would basically make a straight line, but the ones on the edge don't have anything else to make interference, and so you see the spreading out on the edges. And that's what this picture is showing. And of course, this is the argument that got him started, is that if you take an infinitely small one, it spreads out equally in all directions. And so this is referred to as Huygens' principle. And your author then shows you a bunch of these pictures. And in fact, if you look at the one that he's kind of repeating from our sound waves, so going back a semester, he said the same thing happens for sound waves, that the sound comes in and then spreads out. And here's a listener of sound waves, and it looks like this is kind of like inside the room, and the sound waves come out and they spread out, and so somebody who is not in direct line of sight of the door can still hear the sound because the sound waves spread out, they diffract. Light waves do the same thing, although you're going to see how much they diffract really depends on their wavelength. And so things that have small wavelength barely spread out. And remember how small these wavelengths were? Remember back a few moments ago when I was talking about section 1? Remember I said their wavelength is in the nanometers? And that's why most people don't think of light as diffracting, but they always think of sound as diffracting. The truth is they both diffract. But it's really not noticeable until the size of your opening gets to be about the same as the wavelength. And for light waves, that's really small. But for sound waves, that's about the size of a door. And so nobody has any troubles with sound going out a door and spreading out equally. Everybody buys into that. It's light waves that are a little bit more disbelievable. But that's why when we get to the next section, I will show you the diffraction of light. All right, well, now would be a good time to maybe do a couple of examples. So let me go to the end of this chapter. Oops, went too far. 28, 28, 28. And I put here on my list number 2 and number 4. And so number 2 right here says, find the range of visible wavelengths of light when you're in crowned glass. All right, so let me come over here to the board. Let me grab my calculator. I will then leave this first and important equation that's right here on my right. Remember we said the wavelength will shrink up by whatever the index is. And so for visible light, this Roy G. Biv, the red was at 700 nanometers. The violet was at 400 nanometers. If we're in crowned glass, this is now going to be 700 nanometers divided by the index of crowned glass. Now, I don't expect you to memorize the index, so feel free to go back to your book and look up the index of crowned glass. But it's about a 1.5. Usually it's about 1.52 for the middle of the spectrum. Maybe I'll just put a 2 here for a little more completeness. And then 400 nanometers divided by 1.52. And so let me grab my calculator here and go 700 divided by 1.52. And so this would be 460 nanometers. That would be the wavelength of red when it's in the glass. Okay. By the way, in case anybody's asking, it's not like you would see a variation in the color. What you see is when the light actually gets to your eyes. So you could call it whatever you want in the glass. The reality is, what's the wavelength when it gets into the salt water of your eye? And that's always the same. So it can change in the glass and change into the air, but ultimately it's going to change and go into your eye, and that's how you're going to compare colors. So to say the color change is very misleading. Then there's other things involving the energy. So I don't want to say the color changes, but I kind of like the question because it does allow us to take a moment and point out that the wavelength's going to vary a little bit. All right, so this would be 263 nanometers. All right, so visible light would be as low as 263 in glass and as high as 460 in glass. So that's the first example. Let me take a second example. What did I say here? Number 4. So let's read number 4. It says, analyses of the interference effect of a clear solid show that the wavelength of light in a solid is 329 nanometers. Knowing that the light came from it's called a HeNe laser, a helium neon laser, which has a wavelength of 633 in the air. Is this substance zircon, or diamond? And so we know what its wavelength is, both in the air and in this solid. So using this same equation, I'm going to say, maybe I should put here number 4. Did I put here number 2? I should have put number 2. I can then put what it is in the air, which 633 nanometers. And let me come back here. What was it in the solid? 329. And so the N would be 633, and I'll just cancel off nanometers from the beginning here, divided by 329. And so this index of refraction, 633 divided by 329. And that's an index of 1.92. Which I think that's a little low for diamond. I think diamond's up in the 2 range. So I'm not sure what the zircon is, but I have a feeling that it's a zircon. And so let me go back to, let's see, which chapters. And this must be chapter 25, is my guess, where these indexes are all listed. And to wrap up this section, let me just scroll down. I think we got a big table here looking at the indexes. Yeah, this must be it. Let me get that 100%. So here's liquid. Here's diamond. Yeah, so here's my diamond. And I thought diamond was pretty high, 2.4. And so I'm looking at 1.92. Huh. Oh, there it is. It's on the next page. I go, that's weird. They wouldn't list it. I was about to Google it, but there it is, 1.923. Yep. And so I can use the interference of light to decide, is this a real diamond or is this a fake diamond? Right? And so in this case, we used the light, we interfered it, and discovered that what we really have is a fake diamond, or artificial diamond. Well, I shouldn't call it artificial because that's something else, but a fake diamond. So it looks good on jewelry, and inexpensive, but is really not quite the same. Well, let me pause right there. I'll say, hey, Ron, why don't we cut down the camera, because we'll do the next 2 sections after we take a little break. All right, see you guys. Hey, welcome back here. We took a break. Actually, it was a long break because I had to give a lecture for another class, and then we had to do a lab. And anyway, so we're back in the classroom, and I thought we'd go ahead and do the next 2 sections. Let me put them here on the board. Let's go to section 27.3. This is referred to as the Young's double slit. And maybe I'll just kind of spell it out here. So here it is, Young's double slit. And so Young's double slit is, as the name implies, we're going to take 2 small openings and shine light through them. And so they're like vertical cuts. They're literally slits. And there are 2 of them, but they're really close together. You might remember we just had this discussion in the last section, 27.2, Huygens principle. What would happen to light or any wave, it could be sound waves, when it went through a small opening? We can think of that opening as a microscopic source, and the light would spread out. The light would diffract. And so hopefully what we're going to see is the light spreading out from this opening, and at the same time, the light spreading out from that opening. And then we're going to project this light on the screen. And the key understanding of this is that if you were to draw a line right down the middle, and you were to say, look at some point off the center line, the light coming from the top slit would travel a different distance than the light from the bottom slit. And so if you remember that blue, big, long trombone thing. It's called an acoustic interferometer that I was showing you in the last section. We can control then how the waves come together. I'll begin here. So let me come over here to your textbook. I will point out that, okay, here we are, section 3. It's called Young's double slit. And your author does a good job in this picture here that says, okay, how do you actually build this? And so he's got a better 3D picture than my little 2D one. But he says here the light comes in and it enters in the 2 slits at the same time, and then it spreads out. So in other words, if you only had one opening, it would spread out and this whole screen over here would light up. You would have light going in every direction. But the reality is we've got 2 slits. And so when you have the 2 slits, you're going to have both sets of light and you're going to get some interference. All right, well, let me recap what we did in the last section. Your author does a good job. That same picture I was trying to show in the wave nature is that what if you had this? Here's wave 1, here's wave 2. And they're showing the same thing I did, where if you had a crest line up with a crest, the result is a crest that is twice as big. Or a trough line up with a trough, the result is twice as big. And so when waves align themselves, so crests line up with crests, you get a big wave. Now, what this means to our eyes is a big intensity. So 2 waves like this, 2 waves where the crests line up, resulting in something like this, means you're going to get bright light. Sometimes we refer to this as constructive interference. And I think I used that word in the last section. But look down here. The same picture, like I said, I was trying to draw, where if you have this first wave and you combine it with this second wave, notice that the first wave's crests line up with the trough of the second one. So when you add those 2 together, the result down here is 0. In other words, an up plus a down is 0. And this is all the way across. Right here, this trough lines up with this crest, you get 0. A little bit over, you've got this crest lining up with this trough, you get 0. This trough lining up with this crest gives you 0. Crest lining up with trough gives you 0. And so this is destructive interference. And so the resulting wave is what you might call very dim. In fact, it might be so dim we couldn't see it with our eyes. In fact, it might be so dim we'll call it off, dark, no light at all. And so this would be bright and this would be dark. So, like I said, let me start there with just kind of a review of the wave nature. And let me come back over to here and, well, I'll do a little picture, but I think my video I'm about to show you does a better job. But I would say that if you draw a line across here, that you can hopefully see that the light coming from this bottom slit travels this much further than the one at the top. And therefore, the waves that interfere up here on the screen may be something like this. Maybe something like this. I suppose most likely there's something kind of in between. Watch. Let me switch over to a really good animation we've created. And so let me just hit play on this video for a moment. So here's the idea. The waves are coming in, they hit the 2 small openings, and then you can see them spread out. They diffract. And they're going to flow across, and I'll call this the screen. Now let me hit a pause here before this movie goes too far. But the top slit is doing the same thing. The light is spreading out. And what's nice about that is you can see the individual circles around this opening and the individual circles in that opening. And as they get all the way over here to the screen, you will get places like right here, and we've color-coded it with kind of some white light, to say what's going to happen is you're going to get constructive interference, but you're also going to get destructive interference. In fact, there'll be a whole set of these, and that's why we call it an interference fringe pattern. And so let me just play the movie a little bit longer. Oh, actually, I should have paused it right there. Sorry, maybe I'll pause it right there. But if you look at what we'll call the center line, and so halfway between the two slits, straight across, you can see that the distance that the light travels from the top one and the distance from the bottom one are exactly the same. And so in my picture, that point would be right here. And so the distance to here and the distance to here is exactly the same. So therefore I can say that these two waves come together in such a way that the crests would line up with crests and troughs would line up with troughs. I would have constructive interference. This would look very bright on the screen. In fact, I'm going to give it a label and call it 0. You'll see why I give it the label 0 in just a minute. But it really boils down to how much further does one travel than the other. And so in this case, both of the waves travel the same distance, and so I'm going to put m equals to 0. All right. So with that said, I'll go ahead and then kind of notice that as you move up the screen, you may get to some point where this bottom one travels a half a wavelength more than the top one. And therefore, when these waves come together, the crest of one of them is lining up with the trough of the other one. And you're going to get destructive interference. Now, if you go a little bit further up the screen, the bottom one traveling a little bit further than the top one may now be a whole wavelength further. And remember how short these wavelengths are for visible light. So when I say one wavelength further, we're talking about, let's see, and I got, I'll set up a red laser here. So we're talking a distance of about 630 nanometers further. It's not much further, but it is a little bit further. And so it's one wavelength further. I should point out that there's something like 4 million wavelengths from here to the screen in my setup. And so I don't have to go very far at an angle to have just one more wavelength. I already have 4 million from the slit to the screen. Now I'm going to have just one more as I move away. Well, I'm going to label this then as m equaling 1. And what I mean by that is that the bottom one, the distance the bottom one travels is one more wavelength further. And that's why I get constructive interference. Now, maybe I'll stop drawing on the board and come back to my video, because I think my video does a little better job of it than me. And so notice then that my thinking would continue. And so notice the animated video here shows a bright one in the middle, but then it goes dark, and then it goes bright again. And that's what I was just discussing that the reason it gets dark right above this central one is because this light from the bottom slit travels a half a wavelength further than that top one, and I get destructive interference. On the other hand, it gets bright again a little bit further up because the bottom one travels one wavelength further, and that pattern continues. So this would be 1.5 times further for the bottom one to travel. This would be 2 wavelengths further for the bottom one to travel. This would be 2.5, and then eventually we get to 3. And that's what this animation tries to show you when I let it play out, is that here is some good naming for them. The one down the center is called the central maximum, and then of course either direction, and I talked about just going up, but the same logic would happen when you go down. It's just when you go down, the light from the top slit travels a little bit further than the bottom one, but you would get a minimum and then a maximum and then a minimum and then a maximum, and you can see they've labeled them as 1 and 2 and 3, and going the other direction we'll just label them as -1, -2 and -3. So every place where one of the slits travels 1 wavelength further, or 2 wavelengths, or 3 wavelengths, or 4 wavelengths, or 5 wavelengths, we should get constructive interference. Let me keep playing the animation, because here's where I think the author of this animation did a good job. I guess I should go back just a fraction. Whoops. I think I was right about there. Yeah. And so notice many waves, and like I said, for my setup, I'm going to show you with about 4 million waves. And so there's 4 million going here, 4 million going here. We've got a little magnifying glass looking on the screen, and notice they're showing right here how the 2 waves, the crests line up and the troughs line up. And so at the center one, what we call the central, it's going to be bright. And then as we move up the screen, and so right there, I'll pause it, notice what they're trying to show here with the magnifying glass is as you've gone up, if the top one is still 4 million, the bottom one is 4.5 million wavelengths. So when the two come together, and you can kind of see it in the magnifying glass, this right here is the crest of one of them, and this right here is the trough of the other one, and so you get destructive interference. That means it's dim. That means you won't see much light. Oh, I keep bumping this. Could you, yeah, double check the sound there. All right, so then it would get dim. Now, if we continue on, and I'll just kind of let the play, you can see right here, which again, the author of this animation says the first maximum occurs for constructive interference. What it's saying here is, again, if this is 4 million waves, the distance down here is 4,000,001. And that extra 1 means when you take a magnifying glass, you'll see that the 2 waves, the crests line up. And so you get constructive interference. And so this whole pattern is going to continue. I'll let the animation play out a little more now. But as we move up, watch what happens. See, crest and trough lined up, so you get destructive interference. Now you get constructive. We're at the second maximum, so this has 2 more wavelengths further. Now destructive, so this is 2.5 wavelengths further. And now constructive again, third one, and so this is 3 wavelengths further than that one. And so once we understand the concept of it, let me pause the video. Your author says, all right, when are you going to get these maximums or minimums? When are you going to get these bright and dark? And so now we can do a little bit of mathematics here. I can come over here and say, all right, where is it going to be bright? Where is it going to be dark? We could call this maximums and minimums. But if you were following along and it made sense to you, I would say that if the path difference, okay, how much further does the bottom one have to travel compared to the top one? If it's an integer number of wavelengths where m is either 0 or 1 or 2 or 3 or 4, ... Maybe now it's beginning to make more sense why I was labeling these with an integer of 0 and 1 and 2. Because this 0 represents the path difference, not the path difference. Remember, there are 4 million waves here. And so 4 million here and 4 million here, the difference is 0 waves. And so I would say that if that path difference is an integer multiple of wavelengths, okay, you're going to get your constructive interference. You're going to get your bright spots, or what we call the maximum spots. And that means our dark spots would look something like this, m plus a half wavelength. So notice our first dark one, we can set m equals to 0 and then we would have a half. Or we can set m equal to 1 and then this total would be 1.5 wavelengths. And so that's the, I'll call it the fundamental idea behind this double slit. This explains why we get a bright, dark fringe pattern. Now let's come back to the animation over here, because I paused it right where the author has kind of lifted it up to the first minimum, and it's kind of small to see here. It's going to be easier as we get further along, but the author is trying to take a magnifying glass and he's trying to show right here that from here over is 4 million waves, and from here over is also 4 million. This is the extra distance right here. This is that extra 1/2. In fact, I was kind of doing the same thing when I got started, when I drew a line here and was trying to say from this point forward, the distance is the same. And so this right here is that extra path length, okay? That's little extra piece. Well, again, let me come back to the animation because it does a really good job here. So let me play it some more. And so if I hit play, you'll see that the author keeps moving up. Now this extra distance is 1 wavelength. Now it moves up to another dark spot. See, 1.5 wavelengths extra. Over here, 2 wavelengths extra. As it goes up, now we're at 2.5 extra wavelengths. And then finally, 3, where we get construction again. And so now your author says, let's do a little mathematics. And he gives this little symbol here, this extra path length. And I don't know if you're familiar with this symbol. This is the Greek letter delta, the lowercase, not the upper triangular delta that most people are familiar with. But he says, let delta be this extra path length. So coming back over here in my math, I'm going to put delta here. And so I'll say it again. The conceptual idea is if delta, the path difference of the two, is an integer number of wavelengths, you get constructive interference. But if the path difference is an integer and a half, you're going to get destructive interference. And so that's our logic here. Now, let me come back over here because your author does some nice geometry here. He says that if you look at this triangle right here, this path difference, delta, over the separational distance, little d, so I'll put it on the board here, delta over little d, so let me pause right there. Little d then is the distance between the two slits, okay? He says it is the same as, and so he has another triangle highlighted in red, and so he says if you come across here and go up here, these two triangles are similar. And so if you look at the y being the distance up the screen and capital D being the length to the screen, okay? So this is y over capital D. He says, let's use our trigonometry and call that the, I'm sorry, I didn't say that well. Capital D is not quite the length of the screen. Capital D is along this diagonal. But that would be the sine of the angle. And so right here, the sine of the angle, which would be the same as that angle, and he puts here sine theta. What I want to do is kind of equate these two and get path difference is d sine theta, and then use that over here to say d sine theta, or I'll put it down here, d sine theta. And the main piece of math for this section is this. Where are the bright spots on the screen? And so if an integer times the wavelength equals d, the distance between the slits, times sine theta, now theta is this angle on the screen from the slits. If that is true, then this is the place where you will get bright spots on the screen. Constructive interference. On the other hand, if we're looking at a little different angle, and this comes out to be an integer plus a half, if that's true, so in other words, at a slightly different angle than this one would be true, these could not be true at the same angle, but at some other angle, this is where you would get your dark spots. And so these are the two math equations we're going to be using. We're going to be saying, where are the dark spots and where are the bright spots? And this is how we'll do the math. Now, I'll get to some math and show you, but I thought it might be good to actually see this in, I'll call it real life, at least the best I can do on the video. I'm just going to let this play out. I think he just does the rest of the math. So let me call it quits to that and jump back to the book. But then, Ron, I don't know if you can focus well on the screen here, but come over to here and I'm going to just take and show the students that what I have here is a red dot. It's a red laser beam. It's coming from, and maybe for your light source, let me turn that off, but I don't know if you can pick this up, Ron, but here's the laser, and the laser shining over. In fact, I can kind of put my hand here and kind of just chop the beam, and that laser beam then is hitting the screen right here. And so there's my laser beam. And what I'm going to do is take this little instrument. Yeah. So I'm going to take this And this little instrument right here has, well, different slits. This says 1 slit, 2 slits. And so I'm just going to fire the laser beam through my double slit. And I notice the blinds are up a little bit. So let's see how dark it gets when I power down the lights and run. I don't know, will it zoom in and focus on that?
Yeah.
Okay, and I'll even close this up a little bit. It'll be a little darker in here. But looking at this, you can see go bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. And I don't know how well the video camera picks it up, but I could put a little mark here for the central one, and then I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Wow. And now it starts to get too dim and I can't really make it out. I'll turn on the room lights again. And like I said, I'm not sure how many dots you'll be able to see on the video camera. But I would label this then as m equals to 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so that would be what we'd call the 13th fringe. And so using those equations, I would set m equal to 13, or whatever one that they tell me something about. So maybe in the problem they talk about the third bright spot, the third fringe, or maybe they talk about the first or second dark spot. And so that's this idea. Well, if all that made sense, let me continue on with this discussion, because the next section, and I want to kind of talk about this one before we do some example problems, takes this one step further. And so section 4 says, well, what if instead of having 2 slits, you had many, many slits? And the equipment I have to show you, I have about 600 slits. And so what would be different, if anything, when I had many, many slits? And so the next section, 27.4, is saying, okay, let's take a scenario where you have multiple slits. This, by the way, is called then a diffraction grating. And so it kind of looks like a grate, right? It's got all these multiple slits, and hence the name diffraction gradient. Now, what I like in this section is I think your author does a good job here in this picture. Let's see, here's his double slit, and here's all his work on the double slit, which is pretty good. But I think our little animated video is a little better. Let me go a little further. Yeah, it's this picture. So I like this picture because your author does this. He says, even if you have multiple slits, let's just talk about the first 2. For you to get a bright spot, the 2 would be just like the discussion we had. And so I'll put here, where would you get bright? That is, where would they get the maximum? And if you said an integer number of wavelengths equals to d sine theta, and you said, well, let's just say that's what it is for the first two. And so come back to this picture, but I want you to see something here. Let's, for the sake of discussion, let me just look at these bottom two, and this, what your author calls this delta L. Let's just say that extra distance of this top one compared to the bottom one is 1 wavelength. And so these are going off, and they're going to hit the screen, and you're going to have constructive interference between these two. But then notice that if these are equally spaced, then the third one would be 1 wavelength further than the second one, and the second one was already 1 wavelength further than the bottom one. So in other words, the third one is 2 wavelengths further than the bottom one. But remember, that still works. 2 is still meaning the crests line up. So all 3 of these would line up. And so you would have crest lining up with crest and lining up with crest. And so my point is, I'm hoping you can see that if we say wherever 2 of adjacent ones line up, then all of them are going to line up. Because watch this. Let's take the first one. The second one is 1 wavelength further than the first one. But the third one is 2 wavelengths than the first one. And then this one up here is 3 wavelengths more than that one. And this one is 4 wavelengths more than that one. But when all 5 of these then meet, there's going to be this one, and this crest would line up, and this crest would line up, and this crest would line up, and that crest would line up. And so what's nice about this section is I don't really need to derive a new equation here. If the position of where 2 of them give me a bright spot, and I'll come over here and say, this is the equation we just derived for the bright spots when we had 2 slits. I'm going to say, by an extension, these would be the bright spots for multiple slits. Whether they have 3, or as I will show you in a moment, 600 slits. And so here's what's nice. I'll just put a little box around it. This same equation that, well, I just derived, and I will show you examples that I will use for a double slit. I will also use it for multiple slits. I will use it for the diffraction gradient. Now, there is some differences between the double slit and the multiple slit. And it would kind of depend on how many slits you have. But your author does a good job in this graph by showing you this would be the intensity pattern for a double slit. See how m equals 0, this would be the central one, then it would go dark, and then it would go bright again, so this would be the first bright one either direction. If you had, let's see, 1, 2, 3, 4, 5, 6 slits. So this is kind of the pattern you would get from 6 slits. You don't get the 0 kind of in the middle well defined. And what ends up happening when you have, say, 6 slits is you may get one and the other one actually lines up, but the other one's then lining opposite anyways, and you get something quite complicated. So the stuff that is in between the bright spots is really messy. And for this level of class, I'm not even going to try to derive what the intensity would be in the middle, but I do want to point out the intensity in the middle would be very complicated. And in fact, it might be so complicated that I couldn't draw. But B, here's the biggest thing, is notice that there would be kind of this long spacing where you really would have either no light or barely any light, and you probably wouldn't see it with your eyes. And so if I come back and say, hey Ron, let's look again at the double slit. So I'll power down the lights here. Oops, didn't get the light all the way. Let me mute the screen. Let me walk over here. And if you look at this double slit, you'll see that, and I don't know how well this is going to come out on the camera, but between the double slit, there is just a small little space. It'll be right here where it gets dark. And so what you really have is these blobs of brightness that got a fine line of darkness between them. But the multiple slit is exactly the opposite, and that's what I want to point out. So let me turn this back on. Let me power on the room lights. And so again, this is the double slit. And so when you look at it on the screen, you would see this blob of brightness. You would see it really bright and then kind of taper off and then have a sharp line of darkness before you got another blob of brightness. And so if you look across your fringes, you will see mostly light with small strips of darkness. But when you get to the gradient, it reverses. That is, you get a small area of bright, a big area where technically there's a little bit of light, but it's going to be so dim that we're not going to be able to see it with our eyes or with the camera. And so it'll look dark to us, or light is missing, and then it'll get bright again. And you see that well right here. Remember I told you that I was going to shine this laser beam through about 600 slits. I could have overstated that because, wait, this is 1,000 per millimeter, and my laser beam has a diameter probably of a couple of millimeters, so I understated it. I'm probably going to go through 1,000, maybe 2,000 slits. These are so close together that I cannot even see the individual slits. Okay, but what I'm going to do is then set my diffraction gradient here and take one of my laser beams, so I'll use the handheld laser. I'm going to shine it on the whiteboard, and you can see it's red, and because of that, let me find my red marker. And let me find a good target place if I kind of shoot the laser straight through. Maybe somewhere about here. That'll be my target. I'm hoping what you can see, and I might need to turn off a little bit of light here. And I'll tell you where you need to be looking here. This is the center bright one. And then it's dark, 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 and somewhere over here, you'll see the first bright fringe. And so maybe I'll put some objects over here so I can kind of eyeball where it is and write it on the board. Okay, so here I go. I'm going to shine the red beam onto the screen, and it looks like the red dot is right about there. See if I marked it well. Okay, so here I come. I'm going to shine the laser beam through here, and there it is. Looks like I'm a little off. Looks like the red dot is right there. But here's what I'm getting at. If I do the math here, then I would say that if I take the distance between the slits, and in this case, the slits are really close together. I mean, that D is really small compared to the first one I showed you. But there would be some angle, and I would be looking at the first bright one. Now, the next bright one, m equal to 2, would be way over here somewhere. Let's see if we can see it. And so I'm going to shine my laser beam. Oh. Bummer. I don't even see m equal 1 and m equal 2. And it might be that it's not dark enough, but it also might be, okay, and I do want to, yep, okay. Okay. We can't keep going and increasing m forever. I know on the board I put it like m kept going forever and ever and ever, but remember it can only swing 90 degrees. So there's an upper limit to how big m can get. In fact, that's one of the example problems I want to show you. You can only get so big. Now the gradient I'm used to working with, this is a new one, so that kind of threw me off, but the one I'm used to working with, you can see m equal to 2, but not m equal to 3. And it looks like this one, we can't even see m equal to 2. All right, but that being said, watch this for a moment. I'm going to change colors from my red to a green laser beam. And so I'll shine it here on the whiteboard so you can see the green light. But I'm going to come over here and ask you a very important question. Where would the green dot for m equal to 1 be? Now I'm going to shoot the laser beam through the center, and I'm going to shoot the green one right here. And so you can see that for m equals to 0, the straight through shot is the same for all the colors. So if I find my green marker, I'm going to say the green one's going to be right here, right where the red one is. But where would the green one be over here? Now, I hope you remember from our earlier part that the wavelength for green is smaller. Remember the Roy G. Biv? Remember the red has the biggest wavelength. And so as I go through the spectrum here, green is probably around 550. Maybe that's that more yellow, but I'm going to call it 550. And so I'm going to a smaller wavelength. And if you look at the math, smaller wavelength would mean smaller angle. And so the green dot will not show up right here. It's going to show up a little bit inward, right here. And so let's see where it shows up on the screen. So I'm going to take my laser beam. I'm going to fire it right at the X here. And sadly, it's going to be hard to draw. It looked like my green dot showed up right there on the boundary between the two whiteboards. But notice, it's inward a little bit. Okay? And let me just kind of confirm that. Yep, there it is, right on there. Now let me show you the same thing one more time. I got another laser pointer. This is a violet one. And I'm not sure how well violet's going to show up on the video. But there's my violet one. I don't really have a violet marker, but I do have a blue one. So I'm going to use my blue marker to kind of represent my violet. And so I'm going to point out that the blue 0, m equals 0, will go straight through the center. And again, coming back over here to the math, you can see that when m equals to 0, theta would equal 0 for any and every wavelength. So all three of these lasers, the red one, the green one, and this violet one, will all go straight through the center. But then to the sides, where m equals to 1, the one with the shorter wavelength is going to have the smallest angle, and that's what violet is. Remember, violet only has a wavelength of about 400 nanometers. So that would tell me the violet and the blue should kind of be in this range. And so I'm going to come over here and fire. And sure enough, I don't know if you could see it, but it looked like the blue dot was right about there, or the violet dot. Let me kind of set it up again, see if I can get it. Yeah, right on there. Now, of course, I only showed you with 3 colors, but I'm hoping you are getting the impression that if I had all the colors going through this diffraction gradient, the red ones would be over here. So here's the Roy. The orange ones would be right about here. The yellow ones would be here. The green ones are here. The blue is here. The indigo is here. And the violet is there. And so this is trying to say that a diffraction gradient would take white light and basically spread it out into its individual components. Now down the center, they would all hit, and so right here, it would look white. And so if you send white light in, down the center, you get white light. But off to the side, you get a rainbow of colors where the violet is closest to the center, because it's got the smallest wavelength, and red a little bit further out. Oh, that's why your author here has this really nice picture. And he said, this is what you would see if you were to shine white light into your gradient. Now, he doesn't show down the center would be white, and that's too bad. But what he's saying here, and it doesn't matter whether you go up or down, this would be your m equal to 1. You would have your violet light showing up here, and your red light showing up down here, and you have this whole rainbow. And so I showed you this direction to my left. I don't know if you could see it on the video. I didn't pay any attention to it, but there was another set of dots going on over here, and I had another spectrum over here. I just didn't point it out. Your author has another picture that shows this same idea. It's right here, where he says again, and here's where he does do a little better job, but it's kind of small. He says if you go through this diffraction gradient, down the center would be white. And then above and below it would be your first rainbow, m equal to 1. But then you would have a second rainbow, because remember, everything we just did for m equal to 1 would also be true for m equal to 2. Now, as I pointed out, for my particular gradient, I can't get an m equal to 2. And I'll say it again, as they angle over, the most you can get is 90 degrees. So m can go from 1 to 2 to 3, but eventually it stops when you get to 90 degrees. And so this particular one is showing a second order, but it's not showing there'd be a third order, there'd be a fourth order, and if we kind of went along an arch, a fifth order, a sixth order, and eventually you would run out. And so maybe this gradient would only give you m equal to 6 and then no more. But like I said, my lines are really close together, so sadly I'm only able to show you number 1. I wanted to show you number 2, but like I said, I couldn't find my normal gradient, so we went with this one here. Well, as I wrap up our discussion and before we get into some examples, let me point out for you life science people, this happens a lot in the real world or the life science world, and they show this butterfly, a very colorful butterfly. You see it with little tiny hairs, you see it with little tiny feathers, but they really don't have color to them. And so some of these bacterium that look really beautiful under a microscope, or a butterfly that looks really good, you know, as you kind of look at it in the sunlight, or some of these birds and you look at their feathers, they don't really have the color. What they're doing is their little tiny hairs are so close together that they act kind of like multiple slits. And because of that, when you shine the sunlight on them, the colors you see are angled off based upon a diffraction gradient pattern. And so they're trying to show here a butterfly. It looks like they also show some minerals, but I don't know if that's important for you life science people, but this is the Australian opal, and they're beautiful to look at. They really don't have any color when you look at them but under a microscope, but they have the spacing of the crystals are just amazing to look at. All right, well, if all that helped, let me jump down here and go to the end of the chapter, and I've listed up some examples to do. And I'm too far. But starting in about right here, let me do some example calculations, and let me do 2 from each section. And so as I get started here, let me come over here and put these important equations on the board. The first one is d sine theta equals to m lambda, and the other one is d sine theta is equal to m plus a half lambda. And I'll just say this is what we derived first for the double slit. The first one gives us where are the positions of the bright ones and where are the positions of the dark ones. Now, we also said that same formula, d sine theta equals to m lambda, is the place where it works for the bright spots for the grading. And we said that the minimum for the double slit doesn't really work out. Okay, so I'm going to go ahead here and put number 7 and say, let me grab my calculator here and look here at number 7. Number 7 says calculate the angle for the third order maximum of a 580 nanometer wavelength of yellow light following on a double slit. Now, notice they say third order maximum. So I'm going to come over here and grab this equation, the equation that works for the double slit, and the one that gives me maximums. And the fact that they told me that third order, that's what I was talking about, where the m equals 1, 2, 3, or 0, 1, 2, 3. So the 0 is for the central maximum, then we go 1, 2, 3, and this is the third one. So this right here would be 3 times 580 nanometers. Now let me just confirm that I'm remembering the wavelength right. Yeah, 580 nanometers. Now, then they say that it falls on a double slit that is separated by 0.1 millimeters. All right, so 0.1 millimeters. Now, there's two things, well, one thing in particular that's kind of tricky here, and that is watch your units because they don't match. So we need to convert everything either to meters or to nanometers or millimeters, or for that matter, we can convert them to miles. Probably not a good idea to go through that hassle, but I can go ahead and then calculate that angle. So it's pretty easy to convert things to meters, so I'm going to do that. So this is going to be 3 times 580 times 10 to the minus 9 meters. And then I'm going to divide that by 1/10 of a millimeter. And in place of milli, I'm going to put 10 to the minus 3. And that way, I've got both things converted to meters, and then they can cancel off. And so I'll do this in 2 steps. The first one is just to get a number here. So this is 3 times 580 times 10 to the minus 9. Then I will divide it by 0.1 times 10 to the minus 3. And so this is 0.0174. And now, the other tricky thing, this is why I wanted to kind of show you, is I've got to do the inverse operation on my calculator. And I use a lot of radians and degrees, so I'm just going to check that I'm in degrees. Okay, so I'm in degrees. And so I'm going to go inverse sine of my last answer. And so I'm getting about 1 degree. And so you can see the angle is pretty small, very small, and that's kind of normal. If I come back over here to the experiment I was showing you, and it looks like the laser's still on, they come over here, and there's like 4 meters between this double slit and this wall, and the bright spots are pretty close together. They're really, really small in terms of angle. Now, I think my third bright one is probably more than 1 degree, so this one is not a fair representation of mine. But based on the numbers, this is what this one would come out to be. So let me try another one from this section. Let me try number 17 for you. And so 17 is down here at the bottom of this page here. It says, if the first order maximum for a pure wavelength light falling on a double slit is 10 degrees, at what angle is the second order magnitude? And then B, what is the angle of the first minimum? And then C, what is the highest order you can see? All right, well, let me start with this first question, which says, what is the angle of the second one? So I'm going to come over here and write down the same equation I did before, because they're talking, at least at this point, of maximums. And so I'll say it again, that this is the equation we use when we're talking about a double slit and we're talking about maximums. And notice in this that they said the first order maximum of a double slit is 10 degrees. So right here, I would put a 1 for the first order. Then I would say it's sine of 10 degrees. And notice then that they did not give me what the wavelength is or what D is. So I cannot solve for D or lambda individually, but I can solve for D divided by lambda. So I'm going to leave the D here and move the lambda over to here, which means I will leave the 1 and divide it by the sine of 10 degrees. And so I will go 1 and divide by sine of 10 degrees. And so this is about a 5.759. And the reason that's helpful is because, watch here, when they say, at what angle is the second order? I would do this. I would say d sine theta equals, and now I'm going to use the same formula, but I'm looking at the second bright spot, the second order, so m equals to 2 lambda. And if I bring the lambda over here, I get d over lambda sine theta equals to 2. And again, I have to emphasize, I don't know these individually, but I know them collectively, right? This is what this whole calculation was, d over lambda. So this would be 5.759, which then means sine theta would be 2 divided by 5.759. Okay, so 2 divided by my last answer is 0.347. And so my angle then, and so I'll go inverse sine, is 20.3 degrees. And you might have even guessed that it's going to be about double, because you went from m equal to 1 to m equal to. In our equation, we doubled it. Although a sine function is not a linear function, so you would say it'd be close to doubling, but not quite. And sure enough, we went from, excuse me, from 10 up to about a 20.3. All right, well, those are the two that I thought I would do for the double slit. Let's do two more for the diffraction gradient. And so number 23, you can see fits in this category of the multiple slits here. And it says, how many lines per centimeter are there in a diffraction gradient that has a first order maximum for blue light at 470 nanometers at an angle of 25 degrees? All right, well, let me say it again, that we only really have one equation for the diffraction gradient. It's over here. And so for the diffraction gradient, we only have a way to calculate where the bright spots are, because most of everything else is dark spots. So we don't have like the dark spot. We don't have an equation for that. There's a big gap. And so it's bright, dark, 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 bright, dark, 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 bright. And so we've got multiple bright spots, but a big line of dark spots. So again, we don't have an individual dark spot. So that being said, let me go ahead and then put in what I do know. They said the angle was 25 degrees. I think I read first order, right? How many lines per centimeter on our diffraction gradient that have a first order maximum for blue light at 470 nanometers. Now, I have a choice to make. Unlike an earlier problem, like over here, I was dividing two and I needed them to be in the same unit. Here, I guess if I leave it in nanometers, I'm going to get D in nanometers. So I guess I'll do that and switch it if I need to. So this says D equals, and so this would be 470 nanometers over the sine of 25 degrees. So grabbing my calculator, I can put 470 and divide it by the sine of 25. And so this would be 1,112 nanometers. Now, I don't know if that's good or not. Maybe 1.112 micrometers might be a way to label it. Or maybe I should just go 1.112 times 10 to the minus 6 meters. However, I'm not done with the problem, and that's what I want you to see. Look at what they said here. They didn't ask for the distance between the slits. They say, where is it? How many lines per centimeter are there? So you might say what this D is the distance per each slit. What they're asking for is the reciprocal. How many slits per distance? So I'm going to take 1 over D. Because when I take the reciprocal of this, I'm going to get the number of slits per meter. Which I'm still not done because they say how many per centimeter, but it's easy to hit the reciprocal key on my calculator. And so this says, oops, I kind of messed up. Let me try it again. Well, let me just do the reciprocal. 1 divided by 1.112 times 10 to the negative 6. So this is saying that I have 899,280 slits per meter. Now, I'll finish up by doing a conversion by saying I'll put meters on the top, centimeters on the bottom, and then make sure that I am multiplying by a 1. This would then be something like this. So when I divide by 100, I am basically at 8,992 slits per centimeter. All right, well, let's do one more. And there's a class in here in 25 minutes anyways, so that'll work perfect. And so my last one is number 37. And so let me clear a little space here and say, let's do number 37 and call it a wrap before the next class needs this space. So 37 is a little bit further down the road here, and it simply says this. It says, show that a 30,000 lines per centimeter gradient will not produce a maximum in the visible. Oh, shoot. Run. I'm sorry, I need to go back. I got worried about time, but I didn't finish this number 23, did I? Oh, you know which one I didn't finish was 17. Let me backtrack for you guys, sorry. So 17, I did the second order. I could do this. What is the angle for the first minimum? So, sorry about those guys. Here, Ron, come over here. Let's finish 17, because 17 would look like this. We would have the same equation, d over lambda sine theta equals 2 1/2. And so sine theta equals 2, and then this would be 500 and 759, and then this would be 1/2, and so sine theta would equal to that, and theta would equal to this. And so I'm going to take my 1/2, I'm going to divide it by 5.795 here, then I'm going to go inverse sine, and sure enough, it is roughly half of 10 degrees. And so like we mentioned, you would expect it to have doubled here for the second order. Here I expect it to cut in half. But what I really wanted to show you, and this is what reminded me when I came back, is notice that on part C, it says what is the highest order that is possible. And so taking this equation for number 17 again, d sine theta equals to m lambda, and moving the lambda over to here and making this statement that I was trying to say earlier, you cannot have an infinite number of m's. M gets bigger, 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 but eventually the angle gets to 90 degrees and that's where it maxes out. And so for me to solve what the biggest m is, I could put in 5.759 and then put in an angle of 90 degrees. Unfortunately, the sine of 90 degrees is an easy one. And so the largest m could ever be is 5.759. Now, m has to be an integer, so the largest one you would see would be the fifth, because you can't quite see the sixth. Like I said, on my diffraction gradient, sorry, I couldn't show you number 2. I wanted to show you that it does keep repeating. This one repeats quite a bit. Okay, keep that in mind, because what reminded me of that is I wanted to show you how you would calculate the most you can see, because that's what this problem does. Number 37 here for our last example is talking about what's the largest order you can see also. Of course, now they're talking about a diffraction gradient, but it's still the same kind of logic here. And so number 37 says, show that for a 30,000 lines per centimeter gradient will not produce a maximum in the visible. All right, so I'm going to take my equation for maximum for a gradient, which is still over here on the board. And I need to calculate d. D is that distance between two slits. And so it would be 1 over, notice they said 30,000 slits per, and what do they have here? What distance? Per centimeter. Okay. And so this is going to give me the amount of centimeters per slit. And so I'll just put that as 1 divided by 1,000. So the spacing here is 3.33 times 10 to the minus 5. And so that is that reciprocal discussion like we had back here on number 23. And I wanted you to see that as well. But see, now that we know what D is, we can come over here and say, all right, what is the biggest M we can see? And this is the same calculation that I just did for whatever number this was, 17. So if I put in my D, 3.33 times 10 to the minus 5 centimeters, and I say, let's look at 90 degrees, how many orders could I see for a particular wavelength? Okay, now let me come back to the problem, because if you remember our discussion, different wavelengths are going to be at different positions. And so does this say any part of the visible spectrum? I think that's what it's implying. Will not produce maximum in the visible. And so given all the different wavelengths I could use, the one I'm going to choose would be the one that would be the easiest to see. The one that, if you're going to see anything, it's going to be the violet, because the violet is at the smallest wavelength. And so this would be 3.33 times 10 to the minus 5. And if I put centimeters, it would be times 10 to the minus 2 meters. And over here, if I put 400 nanometers, you're going to see that, well, let's see what we get. 1.33 times 10 to the minus 7 divided by the smallest wavelength, 400 nano. I get the biggest m could be is not even a 1. And so this fits in with the same calculation that I could see m equals 0, but I cannot see anything beyond that. Well, let me keep going. How much time do we have here to wrap this up here? But it says, what is the longest wavelength for which it does produce a first order maximum? And so for this calculation, I would say that I already know it's going to be under my 400, but I would put here then d, and I'm going to put sine of 90 degrees equals 1 wavelength. And then, of course, d is 3.33 times 10 to the minus 5 centimeters, which I will write as 10 to the minus 4 meters equals a wavelength. And so this is 3.33 times 10 to the minus 7 meters, or 333 nanometers. And so, yeah, sure enough, it is below the visible spectrum here. It would be ultraviolet. So this gradient would actually work for ultraviolet light, but it's not going to work for visible light. And then it says, what is the greatest number of lines per centimeter a diffraction gradient can have and produce a complete second order? And so, again, maybe a little too quickly, but let's wrap it up here. If I throw in my equation here, it would look like this. We're talking about a diffraction gradient, so it would be d sine theta equals to m lambda. And it says you want to see the whole second order. So the second order is why I pick m equal to 2. And it says complete. So the hardest one to see would be the red at 700 nanometers. And when I say hardest, what I mean, that one's going to be angled out the most. It's why over here, when I did anything, I did the easiest one, violet. So the hardest one, or the furthest one out, is going to be the red. So if you can see the second order red, you could also see the second order green and the second order violet. Okay? And then, of course, you want to just be able to see it. So there's the 90 degrees. And then that gives us the value for d. And then if I take the reciprocal of d, I will get the number of lines. And so real quickly, until the other students can get in here, let me take this, and I can do this one in my head. This is 1400 nanometers, has to be d. And I will then write that as 1.400 times 10 to the minus 9, so I can take the reciprocal. So 1 divided by 1.4 times 10 to the negative 9 means that I get 7.14 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Slits per meter. And a bunch of students want to come in here. So why don't I call it a wrap, and we'll add this to the video, and we'll see you guys soon. Bye now.